Hello, welcome back. I'm Jason. Today I want to do a really cool little demo. You can get these cans of air, these compressed cans of air, and when you allow the gas to come out, you can feel almost immediately the temperature of the can goes down. You can feel it in your hands. So I want to demonstrate that for you, and I want to explain that because it has lots of practical applications. The most important one that I can think of right now is how an air conditioner works. Now before we do that, we're going to look at the slow motion video. I have some slow motion video of the particles coming out here, and we're going to learn a lot about it from the slow motion video. So I'd like to do that first. Let's take a look at what it looks like, and then I'll show you how the temperature goes down, and then we'll talk about exactly why it happens. Now I wanted to start out with a pretty wide shot. You can see the material coming out sputtering at first, and then it reaches a nice steady state flow. This is somewhere around 1,500 frames per second. You can see the narrow jet, but you can also see droplets kind of going sideways and down. Here we're going to inch our way closer with more magnification and a little bit faster frame rate. So this is somewhere around 3,000 frames per second. Notice the little card right below with the lines scribbled on it, the little vertical lines. That's a focusing card. It's very, very difficult with these high magnification, slow motion footage to get them to be in focus. So I kind of use that to help me keep it in focus as I pull the trigger. One thing I think is neat to look at is as the jet forms, little droplets form around the nozzle and kind of dribble and drop down there. And you can see the droplets form and spray off at an angle as the expansion happens. Now I think this is pretty cool personally, but what I really want to do is get as close as I can to it and slow the footage down. So here we go, a higher magnification lens and about 3,500 frames a second. As I pull the trigger, notice the droplets just faintly forming a jet and splashing. And I want you to focus on the expansion of the liquid you see. Notice it's not all flying directly forward. It's coming out at an angle, and you can see the separation between the adjacent droplets getting larger and larger. Keep an eye on the green nozzle. We're going to get a lot closer than this to it. And I'd like you to look at the droplets that are forming on the nozzle itself. You can see that the liquid is kind of coming out and some of it is going into the jet, and you can see the jet is really forming up into a collimated beam, very, very narrow. But you can see that some of the liquid is coming out of the green nozzle and actually wrapping around and kind of flowing backwards and going back towards the can direction. Now what we're going to do here is work our way closer and closer and slow the footage down. And as we do that, I think the most interesting parts of the whole thing is the startup and the stopping. So here in just a second, when the stream starts to cut off, look at the way the droplets form as they stop moving directly in front and start expanding out almost like you're in a spacecraft. Again, the most interesting thing about this is the startup when the liquid first begins to come out, and then also when it shuts off. I think that's when everything is most dynamic. So here I'm about to pull the trigger, and you can see little globules of water start to form in a wispy jet, and you can see very clearly the expansion, not just in the forward direction, but in the up and down direction as the jet begins to take shape. Keep in mind that we're going from nothing to a very powerful jet directed straight ahead over a period of 1 or 2 seconds in real time. So it takes quite a while for the jet to build up in velocity, and so that it sort of stays collimated and pointed in the direction. I think that we've reached basically what the extent of this jet is going to form. Now I think I would say that it's fully directed forward. The other thing I'll say is it was incredibly difficult to get these high magnification shots because it's just very hard to keep something this close up in focus at a high frame rate. So I had to use my focus card and literally try 10 or 15 different times to get the jet to go in the correct direction, to have the camera focus on the jet and get the nozzle in the frame. Very, very difficult to do. So let's go ahead and skip forward to when we shut the jet off and we can see how it terminates. So here I'm about to release my finger from the trigger. The pressure is going to go down, the jet then suddenly disappears, and you can see the expansion of the particles still happening. Look at the droplets forming on the nozzle, still leaking out after everything's stopped. Now this was by far the hardest shot to get. Highest magnification and the highest frame rate. And you can see very clearly when I barely pull the trigger, the liquids start to flow out in sort of fits and starts. Droplets form and start to kind of expand away from the nozzle. We're very far away from forming a collimated jet. You can see in slow motion that this is just a process that takes time to happen. Now the frame rate here is somewhere around 10,000 frames per second, and it took probably 10 takes to get it in focus and to get it quite the way I wanted it to look. I wanted to catch the green nozzle in the frame with it. In fact, I was a little bit disappointed that the green nozzle is at the top of the frame. I really wanted it centered, but honestly, I thought this was about the best I would be able to do here. What I like looking about this is that I can see the liquid coming out, but you can see all of the details in how the pressure is not built up enough yet. So it's kind of using the surface tension. The surface tension is pulling it around the lip of that green nozzle and into the backward direction. Remember, the size of this green nozzle is only maybe, 5-6 millimeters across, very, very small. The other thing I'll say is to get these shots at higher and higher frame rate, again, this is somewhere around 10,000, I think maybe 12,000 frames per second, you have to use quite a bit of light. So studio lights don't cut it. I had to get special, very high power LED lights, and usually 1 or 2 of those lights work pretty well. I got 3 of them, so it's 900 watts of LED lights that are focused behind a dish and illuminating directly on the target. Now you can get some pretty cool slow-mo shots with less light, but at the higher frame rate, it's just too dim unless you just absolutely flood the area with lots and lots and lots of photons. So you can see that there's less splattering going on around the nozzle, and we're at a very tightly collimated, almost like a fire hose of liquid coming out. But you can still see, especially at the top of the frame, the expansion of the liquid going in the up and down direction. It's not directed just in the forward direction. And also notice that at this very high frame rate, you can very clearly see the liquid pooling around the nozzle and kind of flowing backwards. In fact, you can see part of a droplet at the bottom that's formed there. But there's a constant stream of liquid circulating around and going backwards after we start the process. Now again, the goal of this is to try to understand, why does this expansion of material actually cool off the can? Why is the expansion of a gas or a liquid like this actually cause a cooling effect to happen in the first place? So here we are at the end of the road when the pressure goes down, and we can see all of the process winding up, going from a tight high pressure jet of liquid into kind of a diffuse cloud, and then finally it cuts off, and you can see all the dribbling of liquid that happens at the end of the process. I actually firmly think that almost anything that you look at with your everyday eyes can look pretty cool in slow motion. Now, I don't know about you, but even something simple like that propellant coming out, I had to turn the thing upside down because you can't see the air. So instead of shooting the air out, I shoot the propellant out there. And even something simple like that, when you slow down time, is really mesmerizing to look at. You could obviously see a jet of liquid flying out, but you could also see a lot of expansion. You could see it wasn't directed in a straight line, it was kind of fanned out, almost like it was in space and kind of exploding like that. And it's kind of hard to visualize and wrap our brain around why the expansion of a gas is a cooling process. But it's really important to understand, again, for air conditioners and other things. I mean, rocket engines even have expansion of gases, as they generate thrust and propel a spacecraft. So expansion of gases is like used in lots and lots of machinery, right? And so we want to understand how that happens. Now, what I was mesmerized with in general, other than just looking at it, was the way that the liquid on the lip of this thing, the way it kind of pooled around the edge and kind of went backwards even around the lip of it and off the other way. I just never really noticed that at all when you look at it with your naked eye. But when you get right up on top of it, like I was able to do with my zoom lens, with my macro lens, you could see all the intricacies of how some of the fluid comes out and wraps around and goes the other way, which I just think is really counterintuitive and really cool. So how is it that an expansion process like that, you think of an expansion process like what we saw in the slow-mo video. You think of that being almost like an explosion. And you think of explosions as being hot. So it's a little counterintuitive for me to think of an expansion process to be a cooling process. But let me prove it to you. Here is this gas. Here, I think I've let this can here. It's got compressed propellant in it, which will blow gas out the top. And then over here, I have this, this laser infrared thermometer. So when we look at it, right at the green part, hopefully you can see that on the camera there, it's reading about 77.7 degrees right now. This is in Fahrenheit. Sorry, I have it set to Fahrenheit right now. If you don't like that, you can convert it to Celsius. So what I want to do is I want to show you, as I depress the trigger, what does the temperature do? So again, we're starting off at 77.4. Here we go. 3, 2, 1, go. 76, 75, 72, 70, and I'm running out of gas here. 67, 66, and so on. It's actually really cold, especially at the bottom. Man, look at the bottom. The bottom is 24. So right here at the top, you know, you don't see as much action, but down here, 23 Fahrenheit. That's below freezing. So you can actually feel very, very cold. It feels like an ice cube at the bottom there. Why does that expansion process of a gas decrease the temperature of the can? Why does it decrease the temperature of anything? That's what we want to talk about next. I think to motivate the discussion, what I want to do is go in reverse first. We're learning that expanding a gas, allowing it to get bigger, is actually cooling off and decreasing the kinetic energy of each of the molecules of the gas on average, okay? But to understand why that happens, let's instead go in reverse. What does compressing a gas do? When you compress a gas, you actually increase the temperature. And I did another experiment a while back where we actually had a cylinder, and you can use your hand to slam down and actually convert some of the energy of the motion of your hand into raising the kinetic energy of the gas in the cylinder, even to the point where you can ignite a small piece of cotton in the bottom. That's what I have in the bottom there, is a little piece of cotton. And the reason the temperature goes up under compression is because the molecules are bouncing off my, if you pretend my hand is the cylinder face, it's bouncing off all the time going in the opposite direction, trillions of times a second. But if I start compressing and ramming it really, really, really fast and quickly and rapidly, then as a molecule comes in, I'm going to give it more velocity as it bounces off, just like a tennis racket or a ping pong racket hitting a ping pong. As the ball comes in, if you hit it, it's going to bounce off with more velocity. And I'm doing that to trillions and trillions of gas molecules when you compress a cylinder like that. And so by compressing the cylinder, then it increases the temperature because you're increasing the velocity of the gas molecules. Eventually, you get it hot enough to combust the cotton that's in there. But if you noticed really carefully, if you look at that video, as I reach the end of the travel of the cylinder and it kind of bounces off so that the cylinder is beginning the expansion phase, then the pressure of the gas at the bottom is pushing on the cylinder and causing the expansion. So whereas I'm putting energy into the gas with compression on the downstroke, as it bounces off, the gas is doing work on my cylinder, my hand in this case, and the internal energy has to come from somewhere. So the temperature of the gas is going down as the expansion happens on the other side. And that's why the fire goes out right away as soon as I kind of like begin the expansion of it. And the reason that happens is because the temperature of the gas is going down. Same thing I'm talking about here. The temperature of this thing goes down when the gas is expanding. The temperature of the gas in that cylinder is going down when the gas is expanding. And I'm going to talk a lot more in just a second, but in a nutshell, the reason why is that when I compress a gas, I'm literally forcing the work of my hand to go into increasing the kinetic energy of the gas molecules. I'm doing work on the gas. And from thermodynamics, when you do work on a gas, the energy has to go somewhere, and it goes into the internal energy of the molecules, which means they get moving faster. And we perceive that as higher temperature and higher pressure also, right? But whenever the gas expands, then what's going on is the internal energy that was in the gas begins to do work on the piston. So it's reverse. At first, the piston does work on the gas, compressing it, making it hotter. But then it turns around and the gas begins to do work on the piston. And that energy also has to come from somewhere, and it comes from the internal energy of the gas, which means in order to expand the piston, then it has to come from somewhere. It comes from the internal energy of the gas molecules. That's conservation of energy, otherwise known as the laws of thermodynamics, right? Laws of thermodynamics, it sounds so complicated, but it's basically a law of conservation of energy. We talk about work, we talk about heat, which is thermal motion of molecules, and we talk about energy. And in this case, the piston does work on the gas, raising its temperature. It goes into the internal energy of between the gas molecules and their motion, and their rotations also, they're rotating as well. It does work on the gas, raising its temp. Then as it expands, the gas does work on the piston, and that piston is bouncing up because of the internal energy being extracted from the motion, the internal motion there. And so something has to give. It has to come from somewhere. So it comes from the internal energy and the slowing down of the gas molecules. If you want to think about it at a microscopic level, then we can draw the following picture. If this is the piston, right, and this is the cylinder right here, and this is the base over here, I'm doing it sideways here, and I'm shoving it down like this, right, then if the gas molecule was initially here and traveling this way and bounces off, then if the piston weren't moving, it would just bounce off at the same velocity. But if the piston's physically ramming it down, then the velocity this particle bounces off is going to be going much higher because it took some energy from the motion of the piston. So now this molecule has more energy than it did to start with. We've raised the kinetic energy of the gas molecules, thereby raising its temperature, because that is what temperature is. It's a measure of the average kinetic energy of the gas molecules in the chamber. So that's for compression. We make the velocity higher, and so we make the temperature higher. But let's say that we have the situation here where the cylinder is still over here, right? And the cylinder begins to move this way. But it's not moving this way because I'm pulling on it. It's moving this way because the gas it's springing back from the gas. Think about a balloon. If you hold a balloon and you try to compress a balloon, you can feel the springy nature of it. It's going to push back. And so this gas is trying to push back because it's under compression, right? But because we've already heated it up and it's really hot and under a lot of pressure, it has a lot of velocity, right? So the velocity of this gas molecule coming in this way is really, really, really big because I just compressed it. It's a lot. This is velocity here. And so the velocity, you see the arrow is very, very long. So what happens is this molecule hits the face here, and if this thing is allowed to move this way, then it's going to bounce off, but some of the velocity goes into moving it. And so it comes off with a smaller velocity than it had to begin with. That is why gases cool when they expand, even when there's no cylinder. I'll talk about the no cylinder part in just a second. But with a cylinder, it's easy to understand. If you compress it, then the velocity of the cylinder goes into speeding up the molecules of the gas, which makes a higher temperature. And then on the expansion phase, the very high energy of the gas molecules, they're colliding with the cylinder face, with the piston face, and then they're pushing it. And because they're causing motion, they're causing work to be done on the cylinder. The energy comes from somewhere. It has to come from partially from the velocity of the gas molecule. So it bounces off at the same angle you'd expect, but maybe with less energy because some of the energy went into moving it this way. So now the gas has less velocity, less temperature on average. Now that makes sense for a cylinder, but how the heck does it make sense for this? There's no cylinder. So why does it go down in temperature? This thing is still really cold. The temperature is 47.3 degrees, still really cold, right? What happens in the case of this? Well, there's no cylinder, but the gas and the propellant that is under pressure here, when you let it come out, it is still doing work on the environment. Here, the environment is the cylinder, and it's doing work on the environment by moving the cylinder. What is this doing work on? It's doing work on the atmosphere. When it comes out of the chamber, it's pushing against the atmosphere. Right? We don't think about atmospheric pressure because it's always squishing us all the time. But there's 14 pounds of force for every square inch all over your body. That adds up to a lot of pressure. And so when the gas exits the nozzle, it is pushing against the atmosphere. You can think of the atmosphere as being a gigantic cylinder, but not a cylinder made of metal or glass, just a wall of gas that's pushing on it with a pressure. But yet this jet of air, as we saw from the video there, when I turned it upside down, you know, you could see it more readily like that, you know? It's pushing against the atmosphere, right? And it's pushing the air out of the way. So it has to be doing work on the atmosphere. Where does the work come from? It has to come from the internal energy of the storage of the energy and the motion of the molecules, i.e. its temperature. So instead of it bouncing off of a solid wall and doing this, these molecules are bouncing microscopically and encountering resistance to the air that's outside. And they're pushing the air out of the way. So the speed has to come from somewhere. And so it comes from the slowing down of the internal energy. And then that's conducted back through the whole thing inside of here because it's expanding as it comes on out through the whole thing there. Right? So this has applications in refrigeration, I'm going to talk about in just a second. It has applications in rocket engines. You have a big expansion of gases in rocket engines. Has expansions in lots of machinery where gases are doing expansion and rotating machinery. This is what thermodynamics is all about. When we compress gases, they get hotter, and the temperature goes up, I should say. And when we allow the gas to do work on the environment or work on a piston or work on some other machine, then its temperature is going down because that work has to come from somewhere. There's no free lunch in the universe. When we build a machine to extract energy from something and it rotates something like a wheel or something, it has to come from somewhere. And it's coming, in this case, from the internal energy inside or in between the molecules in their thermal motion. So before we close, I want to talk about a couple of different things. Let's talk about air conditioners for just a second. It's a magical device that keeps us cool. In your house, there is a vent that blows nice and cold air on you. In your refrigerator, the inside of the refrigerator gets cold, and so that magically happens somehow. There's no free lunch. It doesn't come from nothing. It comes from the laws of thermodynamics, basically from this process. Here, in a nutshell, in the big picture, is how a refrigerator actually works. What happens is you have some sort of coolant, right? A refrigerant, right? Which is some sort of liquid that can either turn into a vapor or turn into a liquid depending on how much pressure it is under, okay? And what's going on is, what you first do is you take that coolant, it's not so cool at this point, but the coolant, and you compress it with what's called a compressor. And it squeezes it. Now, as you might guess, when you squeeze something, it gets hotter. And so it goes into a liquid state because you're squishing it, but it also gets hotter. And then if you look on the back of your refrigerator, there's a bunch of coils on the back. And the refrigerant circulates through the coils, but it's hot. It's hot and it's under pressure and it's a liquid, right? Because you just compressed it. If you look on the air conditioner of a house, it's the unit that sits outside. There's a lot of grids and coolant loops all over the place. It's called a radiator because it radiates the heat away, and the coolant outside the refrigerator or outside the house then begins to cool off because you just heated it up, remember, through compression. And so you allow it to circulate through these little tubes, and so it gets cool again. It gets cooler than it was, I'll put it that way. Now, here's the thing. It's still at room temperature outside, so you have to make it really cold to make the refrigerator cold. How do you do that? Well, you do that by this. You allow it to go through what's called an expansion valve, and you allow it to expand. The act of expanding the refrigerant and letting it go from a small volume to a larger volume makes it cooler, right? And it gets colder, just like this can got colder. If I put this can, just like it sits, like if I just make it really, really, really cold, it's cold now, I put it inside the refrigerator, it will help cool my ham sandwich inside of there, right? Because it's cold now, right? But so the same thing happens with the refrigerant. You flash it, you make it change state like that, it gets cold. Then it goes into the refrigerator and it circulates through all of the things in the walls of the refrigerator, or it goes into your house where air blows over the coils and makes nice cool air which flows throughout your house. Okay? Now, as the refrigerant makes its way through the refrigerator walls, it absorbs the heat of all the food that's in there, warming it up again. So it's not so effective when you have warm coolant in your refrigerator. So then it exits the refrigerator and it goes and gets compressed again, and that heats it up again, and then it goes back outside to do the whole process all over again. So from the top, it comes out of the fridge, gets compressed, gets hot. It cools down through the grids, through the tubes on the outside, the radiator on the outside. And then it goes through an expansion valve, which flashes it, expands it, makes it cold. It goes into the fridge, it takes the heat away from all the stuff inside that's always trying to warm up when you open the door. And then that coolant is not so cool anymore, so it goes back to the compressor, recompress, and so on. So it's expansion and recompression of this refrigerant over and over again, and it's in a loop. So unless you have a leak, you're never going to lose the refrigerant. Here, I'm losing it because I'm just squirting it. But you know, I'm not going to lose it in a refrigerator because it's in a closed, sealed loop. That's the way it should work, right? And there's different refrigerants and different properties of refrigerant. There's a lot of details there, but that's the basic idea how it works. One thing I want to impart on you is that there's no free lunch, right? You know, some people might think that it sort of like violates entropy or something because the inside of the refrigerator gets cold, you know, and cold things are not moving so much, and so, you know, entropy is somehow less, and, you know, that's like free. It's like entropy is not supposed to go down, or what, you know, how does that work? Well, in order to make this happen, you have to, number one, you have to compress the gas. You have to use electricity to compress the gas. And you're also heating up the environment. That's the big thing. So you are cooling the inside of the refrigerator. But in order to do it, you're basically heating up the outside environment. Remember I said the coolant goes outside to the radiator and it circulates through the tubes? And where do you think that heat goes? Because it was hot out there. It goes into the environment. So you can think of a refrigerator as just a way to move the thermal energy from the inside of the box to the outside. The refrigerator is warm outside the box, but we don't care about that. We want the inside to be cold. And so we're moving the coldness, for lack of a better word, from the inside to the outside. And on top of that, we're spending electricity, we're spending energy to make it happen. So you're burning more energy than you're getting out of this thing and cooling it down is what I'm trying to say. It's not free. It comes from the fact that you're warming up the environment, and you're also using electricity to run the compressor and all the fans and everything else. And so you're always spending more energy than the cooling effect that you're getting on the inside. So it doesn't come from nowhere. Now, the very last thing I'll leave you with is something I learned a long time ago that I think is appropriate for this. I want to teach it to you. It just takes a second. And it's very, it kind of blows your mind a little bit, and it's very helpful as you learn science, especially physics later on. When you think of things under pressure in a can like this, I want you to think of the concept of pressure. Remember we said pressure was force over area. How many newtons per how many square inches or square centimeters? That's what pressure is. But a better way or a different way to think about pressure is to think of an energy density. Energy is the potential to do some sort of work. Density is how much energy or how much of whatever you have per cubic meter or whatever. And the best way or a good way to think of pressure is an energy density. So just because you have something compressed under a high pressure in a small volume, it has a large energy density, which means there's a lot of potential for this thing to do work if it's under pressure and if it's confined in volume there. Let me show you what I mean, right? The pressure in general, the pressure is the force divided by the area. So it might be pounds per square inch, it might be newtons per square meter. That's what it means. Pressure is how many, the force of whatever divided by the area of whatever, okay, like this. However, when you think back to basic science or physics that you might have learned, force you might have learned is related to work. The work done on something is the force multiplied by the distance, or force dotted with distance. All right, but here's a force and here's a force. So I can solve for force here, and I can say that force is equal to the work divided by the distance something moves. And what are the units here? Let's talk about units instead. Well, work is in units of joules. You learned that in physics class. And distance is in units of meters. And so that takes care of this. And the area is in units of square meters. So instead of talking about newtons and square meters or whatever, think about pressure being this force in units of joules per meter, which is a weird unit. I grant you that. But joules per meter divided by area, which is square meters. And as you remember from algebra, the denominator you can take to be over 1. And so you can say that you can you can flip and multiply. This is a fraction division, so you can flip and multiply, which means 1 over meters squared right here. And so the pressure, you can think of it as being joules on the top and meters cubed on the bottom. And this is literally called an energy density. How many joules exist in every cubic meter of space? That's another way to think of pressure. We're always taught, even me, I was taught pressure, force over area, newtons per square meter, pounds per square inch. But when you go through the units, you figure out that it's equivalent to joules per cubic meter. So this can, by virtue of it being under pressure in a certain volume, has a certain energy density. There's a certain amount of energy, potential energy, contained in this tube. And the higher the pressure, then the higher the energy, because if it's a fixed volume, then the higher the energy content must be inside of this thing to give me the same pressure. If I increase the pressure, I must have a higher energy density per cubic meter there. And so whenever I release that energy density goes into expanding the gas as it comes out. And that energy density is energy then used to push against the atmospheric pressure. And then as the pressure goes down, the energy density goes down, right? So as the pressure in this thing goes down, the energy density inside has to go down too, which means it has less potential to do work later on. So when the thing is full of pressure, then it can shoot a jet farther. That's basically what it means. And when it's near empty, you would expect it to shoot a jet not quite as far. An alternative way of thinking about it, when you're solving a physics problem or thinking about physics or whatever, and pressure comes up, force per unit area is good, it's really good, but you can also think of it as energy density, joules per cubic meter, just by virtue of having something under compression, under pressure. And where is the energy coming from in the energy density? It's because of all the collisions of the trillions of gas molecules inside of that volume there. All right, I wanted to take something relatively common, something getting colder when the gas expands, show you that, and I wanted to show you and really dive into why that happens. And I did it with kind of like talking about the expansion and contraction of things and talking a little bit about energy density and other things. And of course, looking at the cool slow motion footage helps us understand how things expand and how it has to be a cooling process. Hope you've enjoyed this. Please let me know, do you like this level of detail? Is it too much? Is it too little? Do you want more of this? Please let me know. I read every single comment. Please drop me a line. Let me know what you think. I will see you in the next one. Learn anything at mathandscience.com.